All right. Hello and welcome to another physics video lecture. Today we're going to be talking about the laws of thermodynamics. So in order to understand these laws, we need to see what thermodynamics is, right? Okay. Now this is another really good example of a big word that we can break down into smaller parts in order to understand, all right? I like to make that division right here, okay? So we've seen therm or thermal before, right? And we know that that has to do with temperature or heat transfer. The new part of this word is dynamics. And I'm sure this is a word that you've heard before or you've understood if something was dynamic, okay? It means it's got a lot of energy, right? And that's exactly what the word dynamic means. It means movement. The opposite of dynamic is to be static. So we'll see that word as well, but just keep that in your mind. So literally, thermodynamics has to do with heat moving, okay? Specifically, how heat is related to energy and specifically the work that is being done, okay? We'll see why in just a second. There are three laws of thermodynamics. There's four laws of thermodynamics that we're going to be looking at, or there are four laws total. We're going to look at three, okay? So we'll get back to all this. Let's just jump in. All right, the first law is actually what's called the zeroth law, and this kind of bugs me. I don't really want to get into it, but most people refer to it as the zeroth law of thermodynamics. And I guess it's called the zeroth law because it's true everywhere, not just in thermodynamics. And here's the law. You may remember this from geometry class, okay? If A equals B and B equals C, then hey, guess what? A equals C, okay? This is true of everything, okay? Not just temperature, okay? And maybe seeing a picture of it will help out, all right? What we're describing here is what's called the transitive property, okay, of geometry. And it makes a lot of sense, okay? Just think about it. If A equals B, let's say A is 60 degrees. That means if A equals B, that means that B is 60 degrees, right? Okay? Now, if B equals C, we already know that A and B are both 60 degrees. If B equals C, C is, you following me? 60 degrees. And that means that A and C are both 60 degrees, which means that they equal each other. It's a pretty, it's something that you kind of just understand, but there is a name for it. It's called the transitive property, and this has to be true in order for any of the other laws of thermodynamics to be true. So just keep this one in the back of your mind, right? If Bob's as tall as Bill, and Bill's as tall as Will, then Will and Bob are the same height. Make sense? All right. So the first law of thermodynamics, okay, this one is actually pretty straightforward. In fact, this is really just a rewording of a law that we've already seen. It's a rewording of the law of conservation of energy. And it says that heat energy, okay, or thermal energy, can never be created or destroyed. We've seen that before. We know this, okay? But it takes it one step further, okay? Whereas other forms of energy can move back and forth freely between different forms of energy, heat energy can only turn into one form of energy, and we can only get heat from one form, and that is kinetic energy, okay? Or, which is the exact same thing as work. So if you remember, work equals the change in kinetic energy. Work done is kinetic energy, okay? Now heat can only turn into work is really another way to describe this law of thermodynamics, okay? Heat energy can only be turned into kinetic energy. Also, we get heat from kinetic energy, whether it's you rubbing your hands together or two tiny little molecules bouncing into each other. Heat energy is always the flow of kinetic energy of the atoms between two objects, all right? It's a very important component of this law right here. You can never create or destroy heat, and the only thing that you can turn heat into or get heat from is kinetic energy or work. Okay? So let's look at an example of this. Let's think about your old car, okay? Now in your car has energy in it right now. My car is not currently on, I hope, fingers crossed. It's just sitting there, but it has energy in it. And that energy comes in the form of gasoline, okay? There's gasoline in my car's engine. And that gasoline has a special type of energy. It has chemical energy, specifically chemical potential energy. Okay, that gasoline has the potential to be turned into another form of energy, all right? Now, how do we unlock the potential energy of gasoline? Well, you need something called a spark plug, because that spark plug creates a little bit of heat. And what that heat does is it lights that gasoline on fire, right? Gasoline is flammable. So the next step here, okay, when you turn your car on, it ignites a spark plug and it converts that gasoline, it converts that chemical potential energy into heat energy, right? There's combustion, okay? Now those atoms are bouncing around super fast, okay? And as we know, when atoms get hotter, right? When you increase the temperature of a substance, its atoms vibrate faster, and when they do that, they bounce off of each other and they expand, okay? Well, that heated air is trapped inside of something called a piston, all right? If you know anything about cars, you know what these are. If you don't, what's happening here is that gasoline ignites this air, and that air is inside of a little piston. That air expands, and there's a little movable slide that now is pushed up. And once you start that movement, you have all these gears and pulleys and things like that that convert that movement into other types of movement, which eventually moves the wheels of the car. And this is how we can turn a liquid into your car moving, which is kind of nuts, okay? So again, we start off with chemical potential energy in the gasoline. A little spark turns that chemical potential energy into heat, and then that heat causes the air to expand because all those atoms are bouncing off each other, going wild, and that expanding air is kinetic energy. It's movement, right? We're physically moving something. And the thing we're moving is called a piston, which in turn moves the wheels. Again, you're seeing the exact same thing here in this picture. Another name for the ignition of the gasoline is what we call combustion, okay? Combustion has a very specific chemical equation. It's actually how things get lit on fire. We're not going to go too deep into that right here, but combustion, all you need is air and some sort of hydrocarbon, okay, like methane or butane, propane. You've heard of those things. You know how you can light those on fire real easy? Okay, a little spark, okay, and a little bit of air. Make sure that you have now fire that is being released and also carbon dioxide and water. But again, we're not going to get too deep into that right now. If you're curious about that, come see me at tutoring, and I'll be happy to explain everything about combustion to you. Here's just another bigger picture of what we just saw. And this actually compares how we use gasoline and oxygen to move the wheels of a car. Is very similar to how your body uses sugar and oxygen in order to move your cells and thus you. So you use chemical potential energy to get turned into heat, which then gets turned into your kinetic energy. Oh, you're a machine. All right, the second law of thermodynamics, this one right here, this one's a little trickier. Okay, the first one's pretty straightforward, but I'm going to do my best to explain this. The reason this is tricky is because the second law of thermodynamics gets very complicated very quickly, all right? It has to do with quantum states when you really start to break it down, but we're going to keep it real simple, right? Don't you worry. So here's what it says. The second law of thermodynamics talks about something called entropy. Now, you probably discussed entropy in your chemistry classes. If you did not, when you see the word entropy, okay, all I want you to think about is the word disorder, okay? Now, this is a simplification of the idea. And again, if you really wanted to understand what entropy was, we're talking about, you know, college, university level textbooks, like whole classes on what this is, all right? But for right now, entropy is disorder, okay? Meaning that things are arranged very far away from each other with no real pattern, all right? And the entropy of a closed system, which is just a group of objects that you're looking at and not including other objects, is always increasing. That sounds weird. What does that mean? Okay, well, let's look at it this way. When energy changes forms from one form to another, which happens literally when you're doing anything, that's what doing something is changing energy from one form to another form, okay? It's never perfect, right? If we think of the example of the car, okay, we are turning the heat from that car into kinetic energy, right? So the heat from that car is supposed to move the piston up and down. That's what moves the wheels of the car. Now, does 100% of that heat get converted into kinetic energy? No. And the reason you know that is because if you touch the hood of your car, you feel some of that heat. If you turn the heater on your car on, you literally feel some of that heat, okay? A lot of that heat is being lost. So the conversion from one form of energy into another is never perfect, okay? You're always going to lose a little bit. And when I say lost, I just means that it just sort of like, think of like a dandelion getting blown. It just sort of goes into other systems. And this is what entropy is, okay? If you want to see it visually, because I think this helps, this is a highly ordered system. See how everything is right in place? This is a highly disordered system. This is very low entropy. This is very high entropy. So the more disorganized something is, the more disorder, the more entropy. And an interesting fact here, because if you're reading this, you're like, hold on, Mr. Norris, you're telling me that the entropy of a system is always increasing. Well, what about the world we live in? That's not true, is it? And the answer is yes. Yes, it is. The total entropy for our universe is always increasing. Now, this is not something that should scare you, but there is this interesting idea, and the base of it is think about this. We said that heat is always transferred between objects of different temperatures, right? Well, eventually, all those objects might become the same temperature, and everything in the universe would stop moving. People will call this the heat death of the universe. It's not predicted to happen for, I don't know, it's like a 1 with 26 zeros after years, but it's a thought, it's an idea right now, and it's kind of insane. And I understand this is crazy stuff to think about. You're like, the universe is going from this to this? Yeah. In fact, we know that the universe is expanding as we see it, right? Now, does this mean that you're going to get Thanos'd away and turned into a bunch of particles? No, that's not what this means, okay? But this is a fundamental law of the world that we live in, okay? And a safer, easier way to think about it is think about your bedroom, okay? Now, if you're like me, you clean your bedroom, okay? I try to. And it takes energy for me to clean my room, right? But let's say that I just spent a bunch of energy cleaning my room, right? Is there any chance that your room is just going to naturally stay clean? And the answer to that is absolutely not. If you live your life, if you do anything in your room is going to become disordered, okay? Naturally, the entropy of your room increases, becomes more disorganized. And the real thing to remember here is that no matter what happens, there is a 0% chance that you're going to show up and your room is going to just spontaneously be clean, okay? In order for your room to be clean, you need energy from an outside source to go in there and clean it. And that outside source is you, right? You need to eat food so you have energy so that you can go and clean your room, all right? And there's a bunch of different examples. Some people will call entropy times arrow. Another example is if you take an egg and drop it, right? You can't unbreak the egg, okay? It is statistically impossible that that egg will ever spontaneously just come back to its original form, right? Time's moving forward, and that has a lot to do with entropy. And again, I understand that starts to get real heady, so when you think about it, just remember, entropy is disorder of a system, okay? A small amount of energy is always going to be lost whenever you have a conversion from one form of energy to another, all right? And the total entropy of our universe is always increasing. So, with that in mind, let's look at this. Which state of matter has the most entropy? Solids, liquids, or gases? Think about it. Have an answer? Did you say gas? Because if you did, you were correct. Gases have the most entropy because their atoms are the most disordered, right? Their atoms are out kind of doing whatever they want. Interesting, right? All right, so the last thing I want to talk about is specific heat capacity. Okay, this is an equation, and I said we don't do a lot of math, but we're just going to look at this briefly. We don't look at this too much, but I want you to understand it. The specific heat of an object is a quality of that object. Specifically, it's the quality of a substance. Okay, so you like gold or iron or lead has a specific heat, and what that specific heat is it's the amount of energy that is needed to raise 1 kilogram of that substance 1 degree Celsius. So let's look at the equation, and we'll talk about it, and we'll do one example, okay? So this is on the first page of your equation sheet. You don't have to remember it. And we got some funky looking stuff going on in here, so let's talk. First, we got Q. Q we have not seen, but Q is heat energy, all right? We measure it in joules, easy enough. M, we've seen before. M is mass, we measure that in kilograms. CP, for reasons I'm not aware of, and I'm not even going to venture a guess, is specific heat capacity, okay? So I got that right there. And then delta T, triangle T, is the change in temperature. So we got the amount of energy, we got how much of the object there is, we got how much of a change in temperature there is, and we have its specific heat, okay? So let's talk about specific heat in the real world, all right? Specific heat can be thought of, if something has a high specific heat, that means that it takes a lot of energy to raise that object's temperature, and it takes a long time for that object to lose that energy and to lower its temperature, all right? And I show you this picture here because here are two substances that are very different from one another, all right? The first substance that I see in this picture is water. Water has a very, very high specific heat, okay? The other part of this picture I see is the sand. And things like sand and asphalt have a very low specific heat. Now, what does that mean? If you've ever been to the beach, okay, when you wake up in the morning, all right, if you go out first thing before the sun comes up, you will notice the sand is very cold, right? But in a couple hours, once the sun's been out for, just a little bit, this sand heats up like that. Okay, it heats up super fast. That's because it has a low specific heat. It only takes a little energy to heat and raise the temperature of the sand. And similarly, by the time the sun goes down, that sand is back to being cold. If you don't go to the beach, just think about the sidewalk or the asphalt outside your house. When it's dark, it's cold, and as soon as the sun comes out, it gets super blazing hot again, right? Well, water is different. If you've never noticed, when you go to the beach, the water is the same temperature pretty much all day. It takes weeks, if not months, to raise or lower the temperature of the water. That's because it has a high specific heat, and it takes a long time to change the water's temperature, okay? This is why your coffee stays hot for quite some time, would be another reason. So let's look at one example here. We're just gonna go through it just so you see one, okay? So if you want to pause the video and see if you can answer this on your own, go for it. Otherwise, let's see what we got. So what is the specific heat capacity? So I already know what we're looking for, so I'm just going to write that down. We're looking for CP, specific heat, of lead. So we're looking for a real specific heat, so you can Google this, right? If it takes 3,840 joules of energy. Okay, so remember, that's our Q, 3,840 joules of energy to raise the temperature of 3 kilograms. So that's our mass, 3 kilograms, from 40 to 50 degrees Celsius. Okay, so I have my initial temperature is 40 degrees, and my final temperature is 50 degrees, okay? When, the first thing we need to find here is our change in temperature, right? So let's do this on here. Change in temperature equals final minus initial, okay? So in this case, that is going to be equal to 40 minus 50 degrees, right? And 40 minus 50, oops, sorry, I have that backwards. What are you doing, Mr. Rose? Our final temperature is 50 minus our initial temperature is 40, which is 10 degrees Celsius. So our change in temperature is 10 degrees, right? We go from 40 to 50. It's a positive 10 because we're going up in temperature. If we're going down in temperature, it would have been 40 minus 50, which would have been negative 10. Back to the problem. All right, here's our equation. Q equals M Cp delta T. Okay, the heat energy equals the mass times the specific heat times the change in temperature. Plug our numbers in. Q is 3,840. That equals 3 times the specific heat times 10. Okay, which again was 50 minus 40. Final minus initial, always. Now the first step here is I need to do my regular old math. And even though they're not next to each other, all three of these things are being multiplied. So I'm going to multiply 3 times 10. So this gives me 3,840 equals 30 times the specific heat, or Cp. Okay? Now, pretty straightforward. We want to get the specific heat by itself. This is multiplication, so we just divide. And we're going to divide by 30, because that's what we want to move. 30 divided by 30 is 1. And I just need to bust out the old calculator. Let's see here. Do I have it? Yep. So we have 3,840 divided by 30. Enter and my answer. And that gives me 128. Okay. So Cp, 128. And there is a unit there. I'm not even going to write it down. I'm not going to write it down. I just want you to know how to find this and that this equation exists and that you can do it. All right? All right, party people, that is it for today's lecture. Again, if you have any questions, email me, find me during tutoring, watch the video again, make sure you take notes, and if you email me a picture of your notes, I'll give you extra credit. All right? Be good, guys.